So to start out with, we're going to just work on constructing a slope field for this differential equation, dy dx equals x minus y. And you probably note right off the bat that this one is very different from the ones we were doing yesterday. For what reason?
It's linear.
Okay, so it's linear in a sense that it doesn't have any squares or any square roots or any of that nonsense that we had before, right?
And it also has an x and a y.
There we go. That's what I was looking for. It also has an x and a y, right? The ones we did yesterday, like root x squared minus x plus 1, not linear for sure, but also just x. And same here with cosine x, also not linear, but also just an x. So here we've now got an x and a y. So when we did the ones yesterday, all we had to do was plug in x values, and then we just made vertical lines that all had those same slopes, right? Like it's like in a vertical column, if x equals 0 gave us 1 in a vertical column where x is 0, we just made a bunch of lines, slope of 1. But now this is going to be a little bit different, right? Because we've got x and y. So both x and y will affect the slope of the line tangent to our function. It'll affect the slope of our derivative. So we'll have to be a little bit more careful. Let's just pick a point to start with. Maybe the origin. How's that sound?
Perfect.
All right, so let's take a look at dy dx at the point 0, 0. What does it equal at 0, 0?
0.
0. Okay, so we'll just go in here at 0, 0 and make 0. Oh, that is almost vertical or almost horizontal. So was that. All right, we'll pretend that's good enough, close enough to horizontal. Now, when else would the slope here, when else would dy dx equal 0? What would have to be true?
X and y are both equal.
Right, x and y would have to be equal to each other because x minus y would give me 0 if they were equal to each other, right? So we could then say something like, well, dy dx equals 0 if x minus y equals 0, or if y equals x. That's a 0. If y equals x, right? And so anywhere along the line y equals x, that's the line y equals x, right? Anywhere along that line, the slopes should be 0. So I'm just going to kind of give myself a bunch of slopes of 0 that way. Seem reasonable?
Yeah.
Yeah. All right, hopefully so. What about if I wanted dy dx to equal some other number? Like, what's another number that's good? 1? That would mean that x minus y needed to equal 1. Well, this is just like you said before, just a linear equation, right? It's the linear equation y equals x minus 1, isn't it? Would everybody agree that x minus y equals 1 would be the same as y equals x minus 1?
Yeah.
Okay. So anywhere along the line y equals x minus 1, we should have slopes of 1. So x minus 1 has the same slope here as this does, right? But it starts down at minus 1. So all of these should be a slope of 1. Good or no?
Yeah.
Yeah.
What about when dy dx equals 2? That'd be if x minus y equals 2, or if y equals x minus 2. So as we go down further, each of these is going to get a little bit steeper. And what's going to happen as we go a little bit lower down here? If I want dy dx to equal 3, that would be y equals x minus 3, right? So each of these is going to get even steeper. And as I continue going down, these are just going to keep getting steeper and steeper and steeper. They're never going to become vertical, right? but they are going to keep getting steeper. Everybody see that? Okay with that?
Yeah.
All right. What about going the other direction, up here above y equals x? What do you think that's going to be? What's going to happen there?
The slope
dy.
will gradually get negative or more steeper in the negative direction.
Exactly. So if we said dy dx equals -1, that would give us x minus y equals -1, or y equals x plus 1. And so we'd just be up one line above, and we now have slopes of -1. Maybe I shouldn't have. I feel like I started that at a not very good spot. There we go.
Wait, is there any specific way you exactly determined the very first part, like in the black pen, like dy over dx 0, 0?
Yeah, I plugged it in up there. I plugged 0 in for x and 0 in for y.
Oh, okay.
And what do you think the next one up would be? It's going to be, instead of -1, we're going to go up to -2. So just a little bit steeper.
Oh wait, so for the 0, 0, like do we always start it at the coordinates of the origin?
I mean, you don't have to start at the origin, but it just seems like an easy value to plug in.
All right.
Start wherever you'd like. And then what's the next one going to be after -2? Should be -3. And I know my lines aren't getting real great here, but that's basically what this is going to end up looking like. And one thing that's important to understand is that when you do a slope field, it's not going to look perfect. And the people that are grading your AP test understand that and know that. They just want it to look generally pretty good. So like mine looks pretty good. You have a general idea of what's happening to that function. For example, if I were to try to plot the solution to this differential equation that went through, I don't know, this point here, it's like 0, 2-ish. Okay. To the left, and start going up and increasing very rapidly here, would flatten out and then start sort of coming towards this slope of 1 there. Or perhaps if I was doing one below, like maybe through this point, these would get very steep. This would start narrowing out and again approach this value of 1 there. Everybody see that?
Yeah.
Cool. So that's generally what the solution to this particular differential equation looks like. We won't have a way to explicitly solve this and get y equals some function in this class. It is possible to do that, but it's for a class called differential equations. That is after you finish your calculus series of 3 classes. So that's the basic idea for that one. Anytime you have a plus or a minus between an x and a y, you kind of want to follow this strategy where you say, all right, well, just make the derivative 0 and figure out what line makes it 0, or figure out what equation you need to follow along and make all the slopes 0. So we said along y equals x, it should always be 0. Then we said along y equals x minus 1, it should always be 1, and so on. X minus 2 for y equals 2, or for dy dx equals 2, and the same thing going. That makes sense? So just set the derivative equal to certain values and figure out a pattern. Good or no?
Good.
And so most, if not all, equations that have both an x and a y will have that like diagonal thing going on.
Yeah, it's most likely that will be the case. Yeah.
Cool.
Any other questions on that one? All right, we're going to do another one that has x and y, but instead of adding or subtracting them, we're going to have division. And so the way we sort of go about doing this one would be the same as if these were being multiplied together also. So we're going to try to construct a slope field for dy dx equals x over 2y. So any thoughts on that? Anybody have an idea of what they think we should do?
Can we still use 0, 0?
Sure, we can start by plugging in 0, 0. What happens if you plug in 0, 0 there?
It's
Undefined.
just 0.
Yeah, you get something that is indeterminate, right? So if you end up with a derivative that is indeterminate, there will be no point on the slope field there. So at 0, 0, we will not put anything there. So then what? Let's think about making this dy dx equal to 0 again. When does dy dx equal 0? If x is what?
If x is 0 and y is not.
Yeah, x is 0, y is not 0. So let's plot all the values where x is 0, but y is not. Well, that'd be here and here and here and here and here. Right? All of these places, yeah? What about, when would it be undefined? When would we have a vertical line?
Everywhere y is 0, but x is not.
Yeah, so this would be undefined if y equals 0, x does not equal 0. So that'd be all of these. And then from there, it becomes a little bit more difficult. So that's kind of the first thing you want to look at is when is it 0 and when is it undefined? Plot those ones first and then sort of fill in the gaps. So if we plugged in the point 1, 1, let's say, that's an easy point to plug in, what would we get?
1/2.
You get a half, right? And so right here at 1, 1, we'll just say this was 1 unit out and this is 1 unit up. We should have a slope that's about a half. Okay. What about as we move to the right here? So as the x values get larger, but the y values stay the same. So if y is still 1, but x is 2, what do we get?
One.
We should get 1, right? So the slope increased a little bit. What about if x is 3, but y is still 1? Is it going to increase some more?
Yes.
Yep, it's going to go up to 3/2, right? That's a little bit too steep there, but let me do something like that. And then out here, it's going to go up to 2. It's going to keep getting steeper, right, as it goes out. What about as it goes to the left? What if I made my x values negative? It's going to do the same thing, except they're all going to be negative values. So this one would be -1/2. This one would be -1, -3/2, -2. Everybody good with that?
Yeah.
Yeah.
All right, what if we move up to where y is 2 and x is 1? What are we going to get?
A fourth.
4, so even less steep. And what if I keep moving up? X is 1, but y is 3. It's going to get even less steep.
6.
Right, we're going to keep getting less and less steep. Try to make those less and less steep. It's sort of hard to see it. Same thing's going to happen over here, right? These are all going to be very shallow slopes. And the same thing is going to happen as we move out. So these will just continue to get larger. So at 2, 2, we should go to about a half. And then it should get a little bit bigger, right? At 3, 2, it should be 3/4, almost to 1, and then at 1. And the same thing going this way. And going out over here at like 2, 3, should be getting a little bit steeper, and a little bit steeper, and a little bit steeper. And the same thing through all of these. They should just, as we go towards the outside part here, they should be getting a little bit steeper each time. And I know, like I said, my lines aren't going to be perfect, but that's generally what it's going to look like. And what about down below the x-axis? You think it's going to follow a similar pattern?
Yes, but
Yeah.
Yeah. When x is positive and y is negative, well, we're going to get the same values that we got here, except they'll all be, down here in this quadrant, they'll be negative. So 1, -1 should be the same as -1, 1. A little bit not steep enough, but something like that. And then it's going to get a little bit steeper as we go out. And the same thing here. And this one will be just slightly less steep to start with. And it will continue to get a little bit steeper as we go. And same thing here, not very steep, little steeper, little steeper, little steeper, and so on. We get the general idea of this.
yeah.
Yeah. What is it sort of starting to look like here? Anybody?
A fancy squished square.
Fancy squished square. All right. Yeah, I would say it sort of looks like a hyperbola-ish, sort of. But let's say we plugged in a point. If we plugged in this point right here, what happens? We end up with it curving up, right? On both sides here. Same thing if we were to plug in something like down here. I don't know, like this point. It's going to get something like that.
So each of those lines are the tangent line for the equation, for the original equation,
solution to
whatever
this.
c.
That's correct.
Cool.
Yeah. And what if I put in, let's say, this point right here? It's going to kind of go up like this. And it would come down here. Now, there's an important thing that we have to note is that, I'm going to make a note on this one right here. Normally, you would think this should curve below here and continue curving down this way, right? But whenever you sketch the solution to a differential equation, we call it the solution curve. You always make it a function. So what that means is I can't extend this down here because then it doesn't pass the vertical line test. I just have to stop there right around the x-axis where it would start curving back and go underneath it again. Make sense?
Yeah. But why do you always make it a function?
Well, it's similar to why we were only looking at like the continuous piece that it, where it was continue, like when we did the initial value stuff, not the initial value stuff, but the basic differential equations before. You're always looking for the continuous piece that includes your initial condition. It's the same kind of idea where that's the only piece of the function that you can include, and it always has to be a function when you solve these differential equations. And so if you get something that's not a function, like, if you get like a circle or something, you can only include either the top half or the bottom half. But it's just the way the differential equations are defined. It's not like, there's no like real, important technical reason behind it. It's just the way it's been defined for years and years and years.
Thank you.
So that's the basics of slope fields. You will definitely need to sketch slope fields, or at least evaluate slope fields and like sketch curves through them on the AP test, one of the two. Usually what they do is they'll just give you a blank coordinate axis and differential equation and put like 12 different dots down on it and say, construct a slope field using these 12 points, and you'll just plug in the points or use one of these patterns to make yourself a nice little slope field. And we'll do problems like that between now and Q4, and also we'll probably do some when we get back from our 9 weeks of not having this class. So any questions on these slope fields and what they are, how to do them, how to construct them, anything about them? All right, let's move forward then and look at what we call separable differential equations. So a separable differential equation is a differential equation that has a product or a quotient of both y and x. So very similar to the one we just did. So the last one we just did, which was what, x over 2y, I think. That one, we, by the end of class today, hopefully, we'll do a problem or two, you would be able to actually explicitly solve that differential equation. Yeah, that would be our hope. And so the way we do that is we just separate the variables. That's why they call them separable differential equations. So if I have dy dx and I have equals something in terms of y times or divided by something in terms of x, all I want to do is just move all the y terms to the side with the dy, and then move the dx to the other side so that it's with all the dx's. And then I just integrate both sides and call it good, basically. Sometimes we'll have to deal with finding constants and all that, but that's the whole basic process. So suppose we had the one we were just dealing with. This is the one we were just dealing with, right? On that slope field.
Yeah.
What you would do is you would get, since this has an x and a y, and it's a quotient of the two of them, you would just get the y over to this side, and you would bring the dx over to this side. So we'd end up with 2y dy equals x dx. Good? Hopefully. And then you would just integrate both sides. So what's the integral of 2y dy?
Y squared.
Y squared plus a constant, right? And what about the integral of x?
X squared over 2 plus a constant.
X squared over 2 plus some constant, exactly. And having a constant on one side and a constant on the other side is kind of redundant, isn't it? Like, I mean, I'm adding a constant here and adding a constant here. I could have just not put one here and just only put one here because I could subtract C2 minus C1 over here. Would you guys agree with that?
Yeah.
So traditionally, we'll just, when we do these separable differential equations and end up with a constant on both sides, rather than writing constant 1 and constant 2 on both sides, we'll just pick a side, put the constant on it. Generally, we put it on the side with the x, with our independent variable, but it doesn't really matter. And so what would we get if we were to square root this? We'd get y equals positive or negative the square root of x squared over 2 plus some constant. Everybody agree with that?
Yeah.
Okay, cool. So let's see what happens when we pick a constant. Anybody got a constant they want to try out there?
5.
5, okay. So if we went into Desmos and we put in y equals the square root of x squared over 2 plus 5, doesn't that look an awful lot like what we had in our slope field for our solution equation?
Yep.
Yep, looks just like it, doesn't it? I mean, we tried to put it through the point 0, 2.236. I think that's exactly what it would look like. And put a negative in front of it, and there it is. There's your negative value for it. Okay. Good or no? So we see that our slope field really did a very good, very accurate job of sketching the solution curve to that differential equation. Good or no?
Good.
And so normally, if we are looking for a particular solution to our differential equation, we've got to find our plus c. We would have to choose the correct plus or minus for the initial condition. And so that's something we'll talk more about as we continue doing this on Tuesday, I guess, since there's no class on Monday. But we're going to do another. We got time to do one more at least. So let's take a look at this one. We want to solve for y if dy dx equals xy, that quantity, squared. So what do you guys think we should do first?
Distribute the squared.
All right, so let's rewrite this as dy dx equals x squared y squared. And then what should we do? What should we do now with it?
Separate it.
Separate it. So bring the dx to the right hand side, so we'll have x squared dx, and bring the y squared to the other side, so we'll have to divide by y squared, which will give us dy over y squared. And then we will just integrate both sides. So on the right hand side, x squared dx should become what?
3 x cubed over 3.
X cubed over 3 plus a constant. And then this one, this is an integral of y to the negative 2, right? If we wanted to, we could do this off to the side here as an integral of y to the negative 2 dy. So what does that become? Y to the negative
Negative 1 over 2.
over negative 1, right?
Oh, yeah.
So that becomes negative 1 over y. Plus a constant, but since we had a constant on both sides, we're just going to put it on one side. Good or no?
Good.
All right. So now, and there are two different sort of ways to go about solving for this constant. Some people prefer to solve for y explicitly first, and then plug in your initial condition and find c. But I think that it is much easier if at this point we take into account our initial condition. So if y is 1 and x is 1, let's plug those in to find c. That gives us negative 1 over 1 equals 1 cubed, or 1 over 3 plus c. So what does it give us as our constant?
Negative 2/3. Oh, never mind. Negative 4/3.
Negative 4/3. That sounds better. All right, so we've now got a constant of negative 4/3. So what we have to do is go back in and say negative 1 over y equals x cubed over 3 minus 4/3. And we then eventually need to solve for y. So I think the easiest way to solve for y is 1, to put this together as x cubed minus 4 over 3. And then what would we need to do? We need to multiply it all by a negative 1. So if I multiplied x cubed minus 4 over 3 by negative 1, that would become what? the negative 1 times the negative 4 would be a positive 4, and the negative 1 times the x cubed would be a negative x cubed. So we'd have 4 minus x cubed over 3. And then what would we do? Just take the reciprocal of both sides.
Yeah.
Cool. Good answer or no? 3 over 4 minus x cubed.
Yes.
Almost. We've forgotten one thing. And that is the interval on which this solution is valid, right? So are there any discontinuities of 3 over 4 minus x cubed?
Yeah.
4 minus x cubed can't be 0, which means that x can't be the cube root of 4. And so the domain of this should be negative infinity to cube root of 4 union cube root of 4 to infinity. That's our domain. Okay. But which one do we choose? We choose the one that includes
Our given point.
our given point, which is the point where x is 1. Where does x equals 1 fall? Between negative infinity and the cube root of 4, or between the cube root of 4 and infinity?
Negative infinity and the cube root of 4.
So we will only choose this piece of it. So we'll say 4 negative infinity to the cube root of 4. Any questions on that? We will do plenty more of these on Tuesday and look at some basic applications of these differential equations on Tuesday as well. But we will stop there for today.